standing on the corner, suitcase in my hand. Jack's in his corset, Jane is in her vest, and me, I'm in a rock and roll band. Huh. Riding a Stud's back at Jim.
Okay, section 1.4 is on perimeter, area, and surface area of similar figures. Wow, that is one long title. Okay, let's remind you of something we did last day, and that was scale factor. And basically, what scale factor is the ratio of corresponding sides in similar figures. So if we were looking for the scale factor of these two shapes here, and let's say this is the image and this is the object, the way we said you did it is to get scale factor. Don't write this, I'm going to erase all this. The way you get scale factor is you take the two corresponding sides, well, we better take these ones up here, they're the only ones we know, and you divide the image, 3, by the object, 1, so you get a scale factor of 3. And what does that mean? It means that this shape is 3 times as big as that shape. Okay, that was with scale factor when we were looking at sides. Today what we're going to look at is we're going to look at perimeter area and surface area of similar figures. So once again, we have similar figures here. Obviously they're similar, they're both squares. They have the same shape, square shape, but they're different sizes. And what I want to look at is, first of all, I want to look at the scale factor. So another way of saying that is I want to look at the ratio of sides, because that's what scale factor is, right? I just said it right here, ratio of sides. I'll also put scale factor in brackets because that's what a ratio of sides is. Okay, so what's the ratio of sides? Well, I just did that. The ratio of sides is 3 to 1 or 1 to 3. It depends which one's the original and which one's the image. Let's just say 1 to 3. Okay, let's pretend that this was the original. So 1 to 3. Okay, now I want to take a look at the ratio of perimeters. So in order to do that, we need to remember what perimeter is. Remember what perimeter is? Perimeter is the distance around the outside of a shape. Like an ant, if it was starting here and walking all the way around the outside, how far did it walk? Okay, well it's pretty easy when you're talking about squares. If I wanted to get the perimeter of the square, I would just think to myself, well this is 1, and another 1, and another 1, and another 1. So the perimeter of this first square is 4. The perimeter of the second square, well the ant would have to walk 3, and another 3, and another 3, and another 3. So 3 times 4, or 4 times 3 I guess, and that is 12. Okay, the first, so the ratio of perimeters is 4 to 12. But what can you do to that answer? You can put it in lowest terms. Divide both of these numbers by 4 and you get 1 to 3. Interesting. The first answer we got 1 to 3, and the second answer we got 1 to 3 when we put it in lowest terms. Okay, let's move on. Let's go to the second one. This time we're looking at circles, and I didn't put the values in here. Let's say that this circle has a radius of 1, and this circle has a radius of 2. And same thing. I want to first of all find the scale factor. Well, for the scale factor here, I wouldn't look at the ratio of sides, because, you know, I mean, you could find, but what would I probably use? I wouldn't say the ratio of sides, I'd say the ratio of radiuses, or radii if you want. It's the same thing. I'll put radii because I like that word, but it's the same as radiuses, more than one radius. And again, I can put in brackets scale factor, because that's really what you're finding when you find the ratio of these things. Okay, again, it could be 1 to 2 or it could be 2 to 1. Let's do the big one first this time. Why not? 2 to 1. Okay, now what we're going to do is we're going to find the ratio of perimeters again. But wait a minute, what do we call the perimeter in a circle? The perimeter is called circumference. Circumference. So, do you remember what the formula is for circumference? The formula for circumference is 2 times pi times r. Or it's also equal to pi times diameter. Why is that? Because if you take 2 r's, 2 times r, well 2 radiuses makes a diameter. So that's why that works. Alright, let's use the first one, use this one since we have radiuses here, or radii. So the first circle we're looking at is the big one. Remember we did the big one first? So we're going 2 times pi times the radius, which is 2. And for the second one, it would be 2, the formula is 2 pi r. It would be, so I'm talking about this circle now. To get the perimeter, or the circumference, it would be 2 times pi times the radius, which is 1. Okay, well, if I multiply that through, I get 4 pi in the first one, and that's compared to 2 pi in the second one. So there you go, there's our relation, there's our ratio. But wait a minute, we can put this in those terms again. First of all, if you look at the numbers, we have a 4 and a 2. We can divide them both by 2. So you're left with a 2 in the first one, and you're left with a 1 in the second one. And you have a pi and a pi. In other words, you can divide both of these by pi, and they just cancel out. So this is it. You have 2 to 1. Look again. The original, the scale factor was 2 to 1, and the ratio of perimeters is also 2 to 1. So this brings us to our first very important point, and here it is. If the scale factor of two similar figures is a to b, then the ratio of the perimeters is also a to b, right? In this case, a to b is 1 to 3, the scale factors, and the ratio of perimeters was also 1 to 3. In this case, the ratio of radii was, or the scale factor, I guess, is 2 to 1, so the ratio of perimeters is also 2 to 1. It's just exactly the same. Okay, that's not too difficult, I guess. Now we're going to look at area. So we're going to get the area of this first square here. So again, I guess I don't need to write it down again, but the ratio of the sides, or the scale factor, is 1 to 3. And if I look at the ratio of areas of these squares, well, remember, area equals length times width. And since length and width are the same with a square, you could also think of it as side squared, right? So anyway, with the first square, since we did do the small one first, it would be 1 times 1, or 1 squared. And the second one would be 3 times 3, or 3 squared. So what values do those give us? Well, 1 squared is 1, and 3 squared is 9. Can we put that in Lowest terms? No. That's already in Lowest terms. Okay, so it's not the same this time. The scale factor of these two squares was 1 to 3, but the ratio of the areas is 1 to 9. Alright, let's see if we can do the same thing over here. The ratio of areas of the circles this time. Ratio of areas. How do you get the area of a circle? Area of a circle is pi times the radius squared. So we started with the big one, right? So we're going to start with this one. So the first one would have pi times the radius, which is 2 squared. And the second one would have pi, this is this one this time, times the radius, which is 1 squared. Okay, I guess I'll work downwards here. So 2 squared is 4, so I get 4 pi. And in the second one, this is a 1 here, right? 1 squared is just 1, so I get 1 pi. Is that in Lowest terms? Not quite. You can divide both of them by pi, so you end up with 4 to 1. The pi's just cancel out. So this is the ratio of areas. Okay, can you see what's happening? For this one, the scale factor, or the ratio of sides, was 1 to 3, but the ratio of areas was 1 to 9. For this one, the ratio of radii, or the scale factor, was 2 to 1, and the ratio of areas is 4 to 1. So what are you doing to these scale factors to get the ratio of areas? You are squaring the numbers. So if the scale factor of two similar figures is a to b, just like we said up here, then the ratio of the areas is not a to b, it's a squared to b squared. You have to square the scale factor to get what the ratio of the areas would be. Alright, one more to go, and that is surface area. So we're just going to do one example here. We're going to find surface area. So first of all, I guess what we should do is find the ratio of sides, just like we did in the last question. The ratio of sides, this is, remember, just another name for the scale factor. Did you just check your phone? That was my phone. Okay, so the ratio of sides is, let's go with the small one first, I guess, 1 to 2. No problem there. Now let's look at the ratio of surface area. Surface areas, I guess. So how do you get the surface area? Well, you get the area of one face, and since it's a cube we're talking about here, How many faces are there? 6, and they're all exactly the same. So you just get the area of one face and multiply by 6. Okay, so to get the area of this face, it would be 1 times 1, and then you're going to multiply that by 6 because there's 6 faces. And we're going to compare that to, in this one, how would you get the area of that face? 2 times 2, and how many faces are there that have that area? 6 as well. So 1 times 1 is 1 times 6 is 6, and 2 times 2 is 4 times 6 is 24. Is that in lowest terms? No, it's not. You can divide them both by 6. 6 divided by 6 is 1, 24 divided by 6 is 4. So our original ratio of sides was 1 to 2, our ratio of surface areas is 1 to 4. Are they the same? No. What's the relationship between this one and this one? It's exactly the same as the last one. It's probably not too surprising. The last one was area, and this is surface area. Whoa, it's way down here. If the scale factor of two similar figures is a to b, then the ratio of the surface areas is a squared to b squared. It's exactly the same as what we wrote here, except instead of saying areas, it says surface areas. Okay, that's basically what you need to know today. If you're talking about perimeters, it's just the same as the scale factor. If you're talking about area or surface area, you have to square them. Let's look at some questions. BC equals 3, so this distance here is 3, and CD is 4. What's the ratio of the perimeter of triangle CDE, the small triangle here, and triangle BDA, which is the big triangle? Okay, well, maybe I'll draw the triangles separately. I told you last time it's often a good thing to do. So there's my big one, and there's the small one. And in the big one, what do we know? Well, we know this whole bottom part here is 7. And in the small one, we know the whole bottom part is just 4. So before we figure out the ratio of the perimeters, let's figure out the ratio of sides. And that's not too bad. We're looking at from CDE, which remember is the small one, CDE, and we're comparing it to BDA, which is the big one. So you got to do it in the right order. The ratio of sides of CDE to BDA is 4 to 7. Those are corresponding sides. It's 4 to 7. That's for the ratio of sides. If we want the ratio of perimeters, what would that be? Well, think back to what we learned in the last page, or on the other side of this page. What do you know about the relationship between the ratio of sides and the ratio of perimeters? They are exactly the same. So the ratio of perimeters would be 4 to 7. That is it. You're finished that question. This one's almost the same, except this time it asks what's the ratio of the areas of CDE to BDA. Alright, what did we learn about the ratio of areas? We learned that it's not exactly the same as the ratio of sides, 4 to 7. It's not exactly the same. What do you have to do? You need to square both of those. So it would be equal to 16 to 49. Alright, let me try to explain exactly what that means. What am I saying here with these numbers? You might be confused, like, okay, I get what you're doing, but I don't understand what the answer is. What I'm saying is, if I figured out what the area was of this small triangle, I figured out the area, right, inside here. Now, I can't do that. I don't have enough information. But let's just say I did. I figured out what the area of this is. And then I compared it to the area of the whole thing, the whole triangle here. I don't know what the values would be right now. I don't have enough information. But what I do know is that the ratio of those would be 16 to 49. So maybe the area down here would be 16, and the area of the whole triangle would be 49. But not necessarily. Maybe the one down here is 8, and which is half as much as 16. And then the whole triangle would be how much? It'd be 24.5 would be half of that. Or maybe the small one has an area of 32, twice as much as this. So then the area of the whole thing would be 98, right? Or maybe it's some really difficult numbers that I don't want to have to figure out. But what I'm saying is the ratio of the small triangle's area to the big triangle's area will always be 16 to 49. Not always, it is 16 to 49. Okay, Jasmine is making a kite from a 2 to 25 scale diagram. The area of the scale diagram is 20 centimeters squared. How much fabric will she need for her kite? Alright, so first of all, this 2 to 25 right here, this is like the ratio of sides, right? So I'm going to write that as a fraction, 2 over 25. And what we're interested in is a different ratio, which is the ratio of areas. So, okay, a couple things. Remember when we talked about scale factors before? The top number is the drawing or the image or the model. So this is the drawing, this is the real thing. So it says the area of a scale diagram is 20 centimeters squared. This 20, is that the drawing or is that the real thing? That's a diagram, it's a drawing. So you have to put 20 up here. And then what we want to know is how much fabric will she need for her kite, for the real kite. So I put an X here. Okay, this seems really easy. It looks like we can just cross multiply and be done. Is that true? No. Why not? Because this here is a scale factor or a ratio of sides. And this here is a ratio of area. Now, what did we learn the relationship is between the ratio of sides and the ratio of area? What do you have to do to the ratio of sides in order to make them equal to the ratio of area? You need to, maybe I'll do it in a different color, you need to square them to make them equal. Right? That's what we saw, is that the ratio of areas is not the same as the ratio of sides or the scale factor. It's the same as when you square the scale factor or you square this ratio of sides. So now you can solve this by cross multiplying. So if we cross multiply this, you're going to multiply those ones together. So you get x equals 20 times 25 squared. You have to square that one. And then you're going to divide it by the one left over up here, which is 2 squared. So that equals 20 times 625 divided by 4. And if you do all that, you will end up with 3,125. And remember, this 20 here was in centimeters squared, so this is also centimeters squared. The real kite would be 3,125 centimeters squared. Little strange, eh? I know it's a little more confusing. This is what I warned you about, that it did get a little confusing today. It's all based on those three relationships we learned back here. 1, 2, 3, wherever it is. There it is. Okay? It's all based on that. Okay, the area of two similar triangles are 36 centimeters squared and 49 centimeters squared. What's the ratio of their heights? So here's we have a ratio of areas. So the ratio is 36 to 49. But again, I'm going to write as a fraction because I find it easier to do my cross multiplying, which I often have to do. So there's my ratio. But remember, this is not a ratio of sides or scale factor. This is a ratio of areas. And what we want to end up with is a ratio of heights. Heights. Well, what's the ratio of heights just going to be equal to? It's just going to, like, a height's a side, right? So we want a ratio of sides. Or in other words, we want the scale factor. So how are we going to figure out what the scale factor is, or the ratio of heights? Well, you could think of it as being like A to B, right? So is it going to be the same? Is it going to be 36 over 49? No, it's not. Why not? Because what we learned is the relationship between the ratio of heights, or sides, I guess, the ratio of sides and the ratio of areas is you need to square these ones in order to make it equal to the ratio of areas. Now, these are wonderful numbers, because which number squared is equal to 36? 6. What number squared is equal to 49? 7. So this is your ratio of heights, or your ratio of sides, or your scale factor even, right? This is the scale factor. If you wanted to know what the ratio of areas is, you would have to square them. 6 squared is 36, 7 squared is 49. So we've just kind of gone backwards here. Again, I know it's a little bit strange. It's hard to get your head around this. It all goes back to those three rules, so keep looking at the rules. Good luck.